All right, continuing on in chapter 13, there is a mechanical equivalent to heat. If you put work into a liquid, shaking, stirring, whatever, however you put that energy in, the response will be heating it up. So we have this example, James Prescott Joule set up this experiment where he had some hanging masses that rotated a stirring mechanism that, with carefully measuring the temperature of the water, could see that it heated up the water. Came up with a mechanical equivalent for what heat is. And so it calls it a kilocalorie. 1 kilocalorie, 1,000 calories of heat energy, is defined as the amount of heat needed to raise the temperature of 1 kilogram of water from 14.5 Celsius to 15.5 Celsius. Now, this is joule we're talking about, so we're actually going to talk about things in joules. 4.186 joules is the same as 1 calorie. Another way of measuring heat is the British thermal unit, but that's something we might see on our power bills, how many BTUs of heat we're using, but not generally in our scientific lives. So capital Q is heat, and that is the energy transferred due to temperature differences. Now, when we build this into thermodynamics, we're going to be using a gas for carrying the heat energy around our system. So we're going to talk about gases a little bit. This will sound familiar to people who have studied chemistry any time in their careers, but don't get too comfortable, because in physics land we do things a little differently. So gases are the easiest state of matter to describe, as all ideal gases exhibit similar behavior, and an ideal gas is a gas that isn't so dense that it's interacting with each other in a way that would make them condense, and that we're going to ignore interactions between molecules and just have the gas interacting with the sides of a container or something. So set up some ground rules here. If the volume of an ideal gas is held constant, then we could say, hey, you know what? If I increase the temperature, the pressure is going to increase. And if I decrease the temperature, the pressure is going to decrease. So we have a sense of a connection there. The rules are fixed volume and a fixed number of molecules. Molecules aren't going in and out. If that happened, then all bets are off. But if we have a contained system with a fixed volume, I can know that if I increase the temperature, the pressure is going to increase. If I decrease the temperature, pressure is going to decrease. If I do add more molecules, then the pressure, if I pump more gas molecules into my basketball, the pressure will increase. If I allow the air to slip out of the basketball, then the pressure would decrease. And if I decide to sit on my basketball, well, in that case, I will find that the volume, if I squish it and the volume gets smaller, then the pressure gets bigger. And if I allow it to expand and the volume gets larger, then the pressure gets smaller. You can put that all together into this thing that will eventually look like the ideal gas law. But wait! What is that K doing there? I'm used to seeing R. Well, let me tell you, in physics land, we're going to use this Boltzmann constant. We can arrive at Boltzmann's constant pretty easily by using Avogadro's number and the universal gas constant. So we'll get to the thing that you're comfortable with. But the deal in physics land is that N, capital N, so not the lowercase n that stands for number of moles, capital N stands for the number of particles. And that's the deal with physics, right? We're talking about these little objects moving around and bouncing off the walls and bouncing off of each other. We don't care how many moles there are. We care about how many different particles there are. So that's the capital N, the number of particles. All right, so PV equals NKT. That's our physics version of the ideal gas law. Pressure in pascals, volume in cubic meters, N, the number of particles, K, Boltzmann's constant, and T, temperature in Kelvin. There is our equation of state for an ideal gas. Now, we know that there are 6.022 times 10 to the 23rd molecules per mole, and so what we're talking about is molecules. But if the situation warrants and we're told, hey, there's 2 moles of a gas in there, then I do 2 times 6.022 times 10 to the 23rd to figure out how many actual molecules I'm talking about, because that's what we'd be interested in physics land. So the gas constant, again, because this is physics and not chemistry, our R is a little bit different. The physics R is 8.31 joules per mole times Kelvin. Those are our units for R in physics land. It's just Avogadro's number times Boltzmann's constant gives us the universal gas constant. So if we were told the atomic or molecular mass of a substance, we could check that out and figure out what the actual mass is. We could figure out how many molecules that is. We're able to use the relationship between the molecular mass and the actual mass that we're given. So if we have 8 grams of helium, then that would be 2 moles of helium. 2 times 6.022 times 10 to the 23rd would tell us how many particles, how many molecules of helium we have. All right, we can take the ideal gas law and take some special cases. If the molecules are fixed and the temperature's fixed, then we have a relationship between pressure and volume that if it's high pressure, be relatively low volume, low pressure, relatively high volume. Similarly, we could look at the relationship between volume and temperature. If we increase the temperature, we're going to increase the volume. If we decrease the temperature, we're going to decrease the volume. We call this one Charles' law. This will bring us up to the kinetic theory of gases. Big stuff. Hang tough for a little bit. We'll talk about it shortly.